In the spring of 2003, there was this 64-year-old medical doctor who traveled from Guangdong province in China down to Hong Kong.
Great.
He was just attending a family wedding. So he checks into room 911 of the Metropole Hotel, and he's feeling slightly unwell, a fever, a dry cough.
Which is, super common.
Exactly. But what neither he nor the global medical community fully understood at that exact moment was that he was actually carrying a novel coronavirus.
Wow.
Yeah. And within just a matter of days, the people who merely walked down that same ninth-floor hallway or who breathed the air circulated by that same ventilation system, they had checked out, boarded airplanes, and seeded explosive outbreaks of severe atypical pneumonia.
In places like Vietnam, Singapore, Canada, all over.
Right. A single node. A single human being in a single building sparked an international crisis that would ultimately cost the global economy an estimated $60 billion.
$60 billion. That event fundamentally shattered the illusion that localized disease remains local. The SARS outbreak of 2003 really demonstrated that our modern, hyper-connected world acts as this massive epidemiological amplifier.
Cases of travel, right.
Exactly. The speed of commercial air travel had finally outpaced the incubation periods of respiratory pathogens. Like, a virus could now cross the globe before a patient ever even spiked a fever.
Which is a terrifying thought. Welcome to the deep dive, everyone. If you are a medical student cramming for your public health modules, or maybe a junior doctor staring at an unfamiliar infectious disease consult, or a public health trainee trying to make sense of shifting population-level data, this conversation is custom-built for you.
We're so glad you're here.
We are dismantling Chapter 8.17 of the Oxford Textbook of Global Public Health. Our mission today is to map out the specific frameworks, the biological mechanisms, and really the systems thinking required to understand emerging and re-emerging infections.
Right. We aren't just going to read you a list of bugs today.
No, definitely not. We are going to look at the structural vulnerabilities of our entire world.
Because that is exactly what this field of medicine demands, Understanding emerging infections requires a continuum of thought.
Yeah.
You really have to trace the hazard to the risk to the exposure to the clinical outcome, the outcome to the necessary intervention, and finally, you evaluate the systemic impact of that intervention.
That's a lot.
It is. It requires integrating molecular biology, clinical medicine, urban planning, ecology, international law, all of it.
So I want to introduce a metaphor to anchor everything we discussed today because I think it perfectly captures the essence of this Oxford chapter.
Let's hear it.
Think of our highly globalized, ecologically disrupted world as an active seismic zone. The microbial shifts, the zoonotic spillovers, the changing climate, those are the tectonic plates constantly grinding against each other beneath our feet.
I like that.
Right. And public health surveillance is our early warning radar. But global preparedness isn't about waiting for the ground to shake and then, running outside in a panic.
Right, that's way too late.
Exactly. Preparedness is upstream, seismic architecture. It is about engineering the building beforehand, designing health systems, supply chains, and diagnostic networks that can actually absorb the kinetic energy of an outbreak without collapsing.
That architectural mindset is it's so crucial because to build a resilient structure, you first have to understand the specific physics of the earthquakes you're trying to withstand.
Yeah, pathogens themselves.
Exactly. You have to understand how they mutate and how they exploit specific vulnerabilities in human populations.
So let's lay the foundational terminology first, because in clinical practice and epidemiological reporting, precision is everything. We frequently conflate the terms emerging and remerging infections, but they actually represent entirely different pathways of hazard.
They really do. According to the textbook, an emerging infection is a disease caused by an organism that is newly identified and not known previously to infect humans.
Or, importantly, it's an organism that is fundamentally changed in its susceptibility to our drugs, right?
Yes, exactly. It's a completely novel variable on the board. Contrast that with a re-emerging infection. The text defines this as an infectious organism that we already knew about, one that has previously infected humans, but has suddenly re-entered human populations or drastically changed its epidemiological footprint.
So it's a known enemy just exploiting a new structural weakness.
Perfect way to put it. And the quintessential textbook case study for reemergence is the diphtheria outbreak in the Russian Federation back in the early 1990s.
Oh, wow. Yeah.
Because from a clinical perspective, we understood Corynebacterium diphtheriae perfectly. We understood the pathophysiology of the exotoxin it produces, the leathery pseudomembrane it forms in the pharynx, and, the life-threatening airway obstruction it causes.
And more importantly, we had a highly effective toxoid vaccine for it.
Right. Diphtheria should have been an architectural problem that we had permanently solved.
But the vaccine only works if the population actually receives it.
Exactly.
The collapse of the Soviet Union triggered this massive political, economic, and social transition. When that overarching systemic architecture crumbled, the logistics cold chains broke down, childhood immunization programs completely lapsed, and population-level immunity just plummeted.
It plummeted below the critical threshold required for herd immunity.
Yeah.
And the pathogen simply walked through the open door. I mean, reported cases of diphtheria in the region jumped from just over 1,200 in 1990 to more than 5,000 in 1993.
That's insane.
It wasn't a mutation in the bacteria that caused the crisis. It was a socioeconomic collapse that destroyed the immunological infrastructure.
Wow. Now, when we look at where the truly novel threats come from, the emerging infections, the textbook provides a pretty staggering statistic. 70%, or potentially even more, of all emerging infections are zoonotic.
Meaning they originate in animal reservoirs.
Right. Because as mammals, we share an enormous amount of physiological and receptor homology with other species. We're living in this dense, interconnected ecological web, and the microbial traffic between species is just relentless.
It really is.
But a spillover event, a virus jumping from a bat or a bird to a human, that doesn't automatically guarantee a pandemic, does it?
No, it does not. And understanding why requires looking at the specific transmissibility of the pathogen once it enters the human host. The text provides a vital framework here. It divides human-to-human transmission into 3 distinct categories.
Okay, let's break those down.
The first is zero to limited transmission. This is where the pathogen can infect a human and often cause catastrophic clinical disease, but it hits a biological dead end. It just cannot independently navigate the jump from the first human host to a second.
And the text uses rabies and variant Creutzfeldt-Jakob disease, or VCJD, as the prime examples here, right?
Yes. With rabies, the virus travels up the peripheral nerves to the central nervous system, causing fatal encephalitis. But humans don't generally bite each other in a way that transfers infectious saliva, so the chain stops.
Thank goodness for that.
Right. But with VCJD, the mechanism is even more insidious because we aren't even dealing with a virus or a bacteria. We are dealing with prions.
Ugh, prions. They are terrifying.
They are fascinating and terrifying from a mechanistic standpoint. A prion is just a misfolded protein. It contains absolutely no genetic material, no DNA, no RNA.
Right.
But when this misfolded protein enters a human brain, it acts as a corrupted template. It physically forces normal, healthy cellular proteins to misfold into the same pathological beta sheet configuration.
Oh.
And these misfolded proteins aggregate, causing the brain tissue to become spongy and just riddled with holes. It is uniformly fatal.
And because it's just a protein, it doesn't trigger a standard immune response.
Yeah.
And it actually survives standard hospital sterilization procedures like autoclaving.
Yeah, a prion can withstand temperatures that would completely incinerate a virus, which is why the only way these dead-end pathogens spread human to human is through direct iatrogenic transmission.
Iatrogenic meaning illness caused by medical examination or treatment.
Exactly. The transmission requires an artificial bridge. For instance, the text notes historical cases where corneal transplants from a donor who died of undiagnosed rabies resulted in the recipient contracting the disease.
Well, that's awful.
Or in the case of VCJD, the misfolded proteins being transmitted through blood transfusions. Outside of those highly specific medical interventions, the pathogen just cannot sustain a chain of infection.
Okay, so the second category outlined in the text is unsustainable transmission. This is where the pathogen secures a temporary foothold in a human population, manages a few generations of spread, but ultimately burns itself out.
Right, and the textbook points to the 2003 monkeypox outbreak in the United States as a classic example of this risk-to-exposure pathway resolving itself.
How did that one play out?
The mechanics of that outbreak perfectly illustrate the chain of events required for a novel exposure. You had Gambian giant rats legally imported from West Africa into the U.S. They were distributed to various pet shops as part of the exotic pet trade. In those holding facilities, they were housed in close proximity to prairie dogs. Animals that are highly susceptible to orthopoxviruses. The rats infected the prairie dogs through respiratory droplets or direct contact, and the prairie dogs subsequently infected the humans who purchased them as pets.
But the human-to-human transmission was incredibly weak, right?
Very weak. The virus caused lesions and febrile illness, but it didn't possess the necessary viral fitness to adapt to sustained human transmission. After 1 or 2 generations of human contact, the outbreak simply ceased. The virulence actually appeared to attenuate as it passed through the human population.
That's fascinating. And the textbook groups the Ebola virus in a similar category of unsustainable transmission, provided that certain conditions are met anyway.
Yes, it does.
And this is where I have to look at the evolutionary biology of the Ebola virus and point out that despite the absolute terror it inspires, it is arguably utilizing a terrible evolutionary strategy.
Really? How so?
Well, a virus's only biological imperative is to replicate and spread to as many hosts as possible, right? Ebola has a short incubation period and causes a profound, rapid progression of severe hemorrhagic fever. It incapacitates and kills its host so quickly that it essentially burns the house down before it can jump to the next neighborhood.
That's a very good point.
I mean, if a patient is bleeding profusely and immobilized by systemic shock, they aren't walking through an airport or sitting in a crowded movie theater spreading respiratory droplets.
Your assessment is epidemiologically sound. Highly lethal, rapid-onset pathogens inherently limit their own basic reproduction number. There are not, because the window of mobility for the infectious host is just so narrow.
Exactly.
If basic public health measures are rapidly deployed, specifically isolation of the sick, contact tracing, and safe burial practices, the transmission chains of Ebola are actually highly vulnerable to disruption. It requires close, unprotected physical contact with infectious bodily fluids to spread. Remove that specific exposure pathway and the virus starves.
Which stands in stark contrast to the third category, sustained transmission. I mean, if Ebola is an evolutionary blunt instrument, HIV is the ultimate stealth operative.
Oh, absolutely. The mechanism of HIV is a masterclass in immune evasion and silent dissemination. HIV is a retrovirus, meaning it uses an enzyme called reverse transcriptase to convert its viral RNA into DNA, which it then physically integrates into the genome of the host's own CD4 immune cells.
It just hides there.
It does. Once integrated, it can lie dormant. The host can remain completely asymptomatic, showing zero clinical signs of disease for years, sometimes a decade.
And during that entire latent period, they are highly infectious. They are living their lives, traveling, forming intimate relationships, completely unaware they are vectors.
Right.
The text notes that HIV is thought to have spilled over from non-human primates in the late 19th or early 20th century. It amplified in the 1970s, but because the clinical presentation of AIDS takes years to develop, the medical community didn't even detect the existence of the virus until the early 1980s.
It completely infiltrated the global population undetected. By the time the first clusters of opportunistic infections like Kaposi sarcoma and pneumocystis pneumonia were recognized in clinical settings, the virus had already established a massive, entrenched global presence.
Wow.
By 2010, long after the transmission mechanisms were understood, the virus was still causing 2.7 million new infections and 1.8 million deaths annually. Stealth, combined with a mode of transmission linked to fundamental human behaviors, ensures an almost permanent state of sustained transmission.
This stealth dynamic brings us to a fundamental conceptual difference the text emphasizes, one that every public health trainee needs to drill into their head: the distinction between a hazard and a risk.
Yes.
We tend to use those words interchangeably in casual conversation, but in epidemiology, conflating them leads to disastrous policy.
It really does. A hazard is the inherent danger or potential for harm present in a specific agent or situation, like the existence of a highly mutated, highly lethal strain of avian influenza replicating in the respiratory tract of a wild aquatic bird in South China is a hazard. It exists. It is dangerous.
Right.
But a risk is a mathematical probability. Risk requires exposure. The risk is the statistical probability that that specific bird will shed the virus into a water source shared by domestic poultry, that a farmer will handle that infected poultry, and that the virus will successfully bind to human respiratory receptors and initiate disease.
I love that distinction. Hazard is the loaded gun sitting on the table. Risk is the probability of someone picking it up and pulling the trigger.
Perfect analogy.
And when we look at the influenza virus, we're looking at a pathogen that is constantly pulling the trigger through two distinct mechanisms of genetic alteration: energetic drift and antigenic shift.
Right. Let's talk about influenza. It's an RNA virus, and its replication enzyme, RNA polymerase, lacks the proofreading ability that DNA polymerases have. So as the virus replicates inside a host cell, it constantly makes small copying errors.
Just constantly mutating.
Yeah, these point mutations accumulate over time, slightly altering the shape of the surface proteins, the hemagglutinin and neuraminidase antigens. This is antigenic drift. It's the reason you need a new flu shot every year. The virus gradually changes its disguise just enough to evade the antibodies your immune system generated last season.
And the text suggests the devastating 1918 influenza pandemic, which killed tens of millions of people, was likely a product of this adaptive mutation. An avian virus circulated in non-human mammals, accumulating these small mutations over time until it gradually attained the specific receptor-binding characteristics necessary to easily enter human respiratory cells and transmit efficiently from person to person.
It learned how to pick the lock.
Exactly. It just kept trying until it fit.
But the 2009 H1N1 pandemic utilized a much more abrupt and violent evolutionary mechanism: antigenic shift or genetic reassortment. The genome of the influenza virus isn't a single continuous strand. It is segmented into 8 separate pieces of RNA.
Like 8 different chapters of an instruction manual.
Exactly. Now, consider the biology of a pig. The respiratory epithelial cells of a pig possess receptor sites that can bind both avian influenza viruses and human influenza viruses. The pig acts as a biological mixing vessel.
Oh, wow.
Yeah. If a single pig cell is simultaneously infected by an avian flu virus and a human flu virus, those individual RNA segments replicate and float around in the host cell cytoplasm. When the new virions are being assembled to exit the cell, the segments get shuffled together.
That's terrifying.
The virus that erupts from that cell might contain 3 segments from the avian strain, 4 from the human strain, and 1 from a swine strain.
So it's a completely novel combination of cards that the human immune system has never played against.
Precisely.
The 2009 H1N1 virus was a quadruple reassortant. It contained genetic material from North American swine, Eurasian swine, North American avian, and human influenza viruses. The hazard was the mixing vessel of the agricultural system. The risk materialized when that novel reassortant virus found its way into a dense, immunologically naive human population.
And that transition from the biology of the virus to the environment of the human population is the critical pivot point of this entire chapter. A pathogen's evolutionary brilliance, its reassortment, its latency, its virulence, is only half the equation.
What's the other half?
The pathogen requires an enabler. It requires structural vulnerabilities in human society to amplify its reach.
Which shifts our focus from the microbial earthquake to the building itself. Let's move to Section 2. When we look at the breakdown of modern public health infrastructure and the consequences of rapid, unplanned urbanization, the data is staggering.
It really is.
The textbook details the global resurgence of the Aedes aegypti mosquito and how changes in human consumer behavior essentially rolled out the red carpet for this vector.
Right. To understand the resurgence, you have to understand the entomology of Aedes aegypti. Unlike many mosquito species that breed in natural bodies of water like swamps or lakes, Aedes aegypti is a container breeder.
A container breeder?
Yes. It has evolved to lay its eggs on the inner walls of artificial water-holding containers. During the mid-20th century, concerted vector control campaigns significantly suppressed mosquito populations in many parts of the world. But in the 1970s, as global priorities shifted and funding dried up, those public health programs deteriorated.
Then concurrently, the developing world underwent an explosion of rapid, unplanned urbanization. Millions of people migrated from rural areas into densely packed city centers that completely lacked adequate municipal sanitation or piped water infrastructure.
Right.
And crucially, modern consumer habits arrived.
We introduced non-biodegradable waste into these environments on an unprecedented scale. Discarded automobile tires, plastic food containers, tin cans, discarded household appliances. When the rains come, these items fill with stagnant water, creating millions of perfect, predator-free microhabitats for the Aedes mosquito to breed.
Wow, we literally built them homes.
We did. Furthermore, because these communities lack reliable piped water, residents are forced to store drinking water in open drums inside their homes. Aedes aegypti prefers to bite during the daytime, and it strongly prefers human blood. We inadvertently engineered the perfect ecosystem for the vector to thrive in intimate proximity to the human host.
And the epidemiological outcome of that infrastructure failure is dengue fever. Prior to 1970, the textbook notes that only 9 countries, primarily in Latin America, experienced severe outbreaks of dengue. Today, because we built this urban breeding infrastructure, dengue is endemic in more than 100 countries across the Americas, Southeast Asia, and the Western Pacific.
That's a massive jump.
We're looking at estimates of 50 to 100 million infections globally every single year.
And the clinical reality of dengue is complex. It's caused by 4 distinct serotypes of the virus. Infection with one serotype provides lifelong immunity to that specific serotype, but only temporary partial immunity to the others.
Okay.
In fact, if you are subsequently infected by a different serotype, you are at high risk for antibody-dependent enhancement.
What does that mean?
Your pre-existing antibodies bind to the new virus but fail to neutralize it. Instead, they actually help the virus enter your macrophages, leading to massive viral replication, vascular leakage, and life-threatening severe dengue or dengue hemorrhagic fever.
That's just wild. The body's own defense makes it worse.
Exactly.
And the vector didn't stop with dengue. In 2005, the chikungunya virus, an alpha virus that causes debilitating, long-lasting joint pain, emerged from East Africa. It spread through the islands of the southern Indian Ocean. But here's where the story takes a fascinating molecular turn.
Oh, this is a great example.
A single-point mutation occurred in the envelope protein of the chikungunya virus. This tiny genetic shift allowed the virus to be highly efficiently transmitted not just by Aedes aegypti, but also by Aedes albopictus, the Asian tiger mosquito, a species that can survive in much cooler, temperate climates.
That single viral mutation, combined with the global shipping trade moving dormant mosquito eggs inside used tires, fundamentally changed the disease landscape. By 2007, chikungunya had spread north into Europe, causing an outbreak of hundreds of infections in the Emilia-Romagna region of Italy.
In Italy. Wow.
Yeah. The local infrastructure failed to control the invasive vector, the vector multiplied, the virus mutated to exploit the new vector, and a tropical disease suddenly erupted in a temperate European zone.
We tend to view hospitals and clinics as sanctuaries, the ultimate defensive architecture. But structurally, if the basic protocols of infection control break down, a hospital flips from a sanctuary into an amplification node.
It really does.
The textbook outlines several devastating lapses in basic medical safety procedures that turned healthcare facilities into vectors.
Nosocomial or hospital-acquired transmission is a profound systemic failure. In the late 1980s and early 1990s, we saw horrific outbreaks of HIV in pediatric populations in the former USSR and Romania. Over 250 children were infected.
How did that happen?
The mechanism was the reuse of unsterilized syringes and needles, coupled with the practice of microtransfusions of blood to treat malnutrition and anemia in crowded orphanages and pediatric wards. A lack of basic commodities, sterile needles, transformed the medical system into an engine of transmission.
That is just heartbreaking. And we saw the exact same dynamic amplify the lethality of Ebola. In the 1976 outbreak in Yambuku, Zaire, and the 1995 outbreak in Kikwit, Democratic Republic of Congo, the index cases were brought to local hospitals. But those hospitals lacked the resources for barrier nursing. No gloves, no gowns, no face shields. They were reusing a handful of syringes for the entire ward without proper sterilization. The virus was mechanically injected into other patients, and healthcare workers who were providing intimate, unprotected care were bathed in highly infectious bodily fluids. The infrastructure didn't just fail to stop the virus, it actively facilitated its spread out into the wider community.
And we must also examine the architecture of our food supply. The textbook presents the emergence of bovine spongiform encephalopathy, BSE, or mad cow disease, in the United Kingdom as a prime example of agricultural policy inadvertently creating a biological hazard.
And again, the mechanism here revolves around the resilience of prions. We were actively feeding herbivores to herbivores.
Precisely. The agricultural industry utilizes a process called rendering to convert animal carcasses and slaughterhouse waste into usable products, including meat and bone meal, which is then used as a high-protein supplement in livestock feed. Over a 10-year period prior to the crisis, the rendering industry altered its processing methods.
To save money, I'm guessing.
Yes. To cut energy costs, they lowered the temperatures used in the process and removed certain hydrocarbon solvent extraction steps.
But a prion doesn't care about a mild drop in temperature. It requires incinerator-level heat to denature.
Right. So by lowering the processing standards, the rendered parts of cattle that were unknowingly infected with the BSE prion remained highly infectious.
Ugh.
This contaminated meat and bone meal was fed back to healthy cattle, creating a massive closed-loop amplification cycle.
Yeah.
The prevalence of the disease in the national herds skyrocketed, and eventually the prion crossed the species barrier. Humans consuming beef products derived from the central nervous system tissue of these infected animals developed variant Creutzfeldt-Jakob disease, a fatal neurodegenerative condition. An economic decision in the rendering plant completely bypassed the biological safeguards of the food chain.
Which logically forces us to look at the broader economic impact of these outbreaks. The textbook breaks down the cost of these events, and the numbers defy comprehension. When an emerging pathogen hits a globalized society, the financial devastation is absolute. But it's not the direct medical costs, the hospital beds, the ventilators, the IV fluids that bankrupt a nation, right?
No, not at all. The economic modeling of outbreaks divides the burden into direct, indirect, and intangible costs. The direct costs are indeed the medical care. The intangible costs represent the profound tragedy of human suffering, the loss of life, and the fracturing of community trust.
But the indirect costs?
The indirect costs are where the macroscopic economic architecture collapses. We are talking about the cascading effects of massive absenteeism from work, the closure of schools forcing parents to stay home, the total cessation of local retail commerce, and crippling drops in international tourism and trade.
And the SARS outbreak of 2003 is the textbook's ultimate proof of concept for this. Globally, there were fewer than 9,000 confirmed cases. In the grand scheme of global morbidity, 9,000 cases is a statistical anomaly.
Barely a blip.
Yet that outbreak cost Asian countries an estimated $18 billion in GDP and up to $60 billion in gross expenditure and business losses. A respiratory virus with fewer than 9,000 cases halted the economic engine of a continent.
Because the variable driving those indirect costs is human psychology. Fear and misinformation drive economic collapse far more rapidly than the pathophysiology of the virus itself. Behavior modification happens instantly.
Like what happened with H1N1.
Exactly. During the 2009 H1N1 influenza pandemic, because the media colloquially labeled the virus swine flu, consumers globally avoided purchasing and consuming pork. This caused massive financial devastation to the agricultural sector, despite the irrefutable biological fact that the virus was not transmitted through the consumption of cooked pork.
We saw the exact same behavioral panic in 2011 during the E. coli 0104 outbreak in Europe. Early, speculative reports suggested the bacteria was linked to Spanish cucumbers. Consumers completely boycotted fresh vegetables across the continent overnight. The agricultural supply chain was paralyzed. The fear of exposure fundamentally overrides rational data.
The textbook offers a profound contrast to illustrate the scale of vulnerability in a globalized system. In 1998, Tanzania experienced a severe reemergence of cholera. The economic loss to the country was estimated at $36 million, a catastrophic blow to an emerging economy. But compare that local crisis to the UK's BSE crisis in the 1990s.
Okay.
The emergence of mad cow disease cost the UK an estimated $39 billion.
1,000 times the economic damage.
Yes, because the BSE crisis struck at the very heart of massive, heavily integrated global agricultural export markets. When a pathogen threatens a multinational supply chain, the financial ruin is amplified exponentially by international trade bans. The local failure dictates the global cost.
That makes sense. Now, if we step even further back from the hospitals and the agricultural markets, the textbook forces us to look at the planet itself, the natural world. We have mapped the urban vulnerabilities. Now we must examine the wild interfaces.
Section 3.
Yes, Section 3. Anthropogenic activities, specifically massive ecological disruptions like deforestation and the sweeping impacts of climate change, are profoundly altering the dynamics of disease transmission.
This is the epidemiological concept of the ecotone, the transitional area of vegetation between two different plant communities, like a forest and a clearing. These zones are rich in biodiversity, but they're also zones of intense microbial exchange.
Okay.
When human industry aggressively drives bulldozers into deep forest environments, we are forcefully altering ecosystems. We are destroying the natural habitats of wildlife reservoirs, forcing them to migrate, and pushing them into dense, unnatural proximity with agricultural livestock and human settlements. Deforestation is a mechanism of viral displacement.
The emergence of the Nipah virus in Malaysia in 1998 and 1999 is the definitive, horrifying case study of this mechanism.
To understand Nipah, you must understand the biology of its natural reservoir. The Pteropus fruit bat or the flying fox. Bats are unique mammals. The act of sustained flight requires a massive metabolic rate, which raises their internal body temperature to levels that would constitute a severe fever in a human.
Oh, interesting.
Because of this, bats have evolved specialized immune responses, including unique interferon pathways that dampen inflammation and allow them to tolerate the presence of highly virulent viruses without developing clinical disease. They are perfect flying reservoirs.
And in Malaysia, vast tracts of primeval forest were being cleared for agricultural and commercial purposes. We destroyed the bats' natural foraging grounds. The bats, facing starvation, were pushed to the edges of the remaining forest, directly into areas where massive industrial-scale pig farms had been established.
Right.
And the farmers had planted fruit trees around the pig enclosures to provide shade and extra income.
The ecological trap was set. The bats congregated in the fruit trees overhanging the pigsties. They ate the fruit, and as they fed, they dropped half-eaten, saliva-laden fruit and guano down into the enclosures. The Nipah virus is actively excreted in bat saliva and urine.
And the pigs, being omnivorous scavengers, ate the contaminated fruit.
Exactly.
And this is where the mammalian biology amplifies the disaster. The pig's respiratory tract is highly susceptible to the Nipah virus. The pigs developed a severe respiratory illness characterized by a loud barking cough. Because they were packed by the thousands into high-density industrial pens, the virus swept through the herds with terrifying speed, amplifying the viral load in the environment by orders of magnitude.
The pigs served as the ultimate amplification host. The slaughterhouse workers and farmers laboring in these enclosed, highly contaminated spaces inhaled the aerosolized virus. The spillover resulted in approximately 250 human infections, presenting as a severe, rapidly progressing viral encephalitis.
And the mortality rate.
The case fatality rate was near 40%. To stop the outbreak, the government had to cull over 1 million pigs, devastating the local economy.
The textbook also details Nipah outbreaks in Bangladesh occurring regularly between 2001 and 2009. But the epidemiological pathway there was entirely different, right? There were no pig farms acting as amplifiers. The mechanism was direct.
In Bangladesh, the transmission pathway bypassed the agricultural intermediary entirely. The local population harvests sap from date palm trees to produce a traditional sweet drink and palm wine. They tap the trees and leave collection pots hanging overnight, but the Terapus fruit bats also feed on the sugary sap. At night, the bats visit the taps, drink from the stream, and contaminate the collection pots with their saliva or urine. The thermal characteristics of the cool night air preserve the virus in the sap. The following morning, humans consume the raw, unpasteurized sap, directly ingesting the virus.
So if we understand these exposure pathways so clearly, if we know that encroaching on the rainforests of West Africa increases the risk of Lassa fever from displaced rodents, or that clearing forests in Malaysia triggers Nipah spillovers from bats, shouldn't urban planning and agricultural zoning inherently be public health disciplines?
Yes, absolutely.
It just feels like our current medical system is obsessively focused on treating the symptom in the ICU while completely ignoring the bulldozer clearing the forest.
That is the core argument of the textbook systems thinking approach. Environmental policy is public health policy. The emergence of Chagas disease in Latin America further underscores this.
How so?
The disease is caused by the parasite Trypanosoma cruzi, which is transmitted by the triatamine bug, the kissing bug. Historically, this bug fed on wild animals in sylvatic, deep forest environments, but massive systemic deforestation eradicated their natural food sources. The bug populations were forced to migrate to survive.
They adapted. They moved into the cracks and crevices of poorly constructed rural and peri-urban human dwellings. They shifted their feeding behavior from wild animals to domestic livestock and sleeping humans. We essentially bulldozed their house, so they moved into ours.
That's exactly what happened.
Deforestation transformed Chagas from a rare sylvatic infection into a widespread urban disease, which can now even be transmitted horizontally through the blood transfusion supply. We engineered our own exposure.
And it is not just bulldozers that are altering the ecotone. The climate itself is shifting, causing profound vector redistribution. The textbook details how climate change and extreme weather events are actively expanding the geographical footprints of endemic diseases.
And the meningitis belt in sub-Saharan Africa is a perfect physiological example of this. Epidemic outbreaks of Neisseria meningititis traditionally occur in a very specific, narrow band of dry, dusty territory. But why? What is the mechanism linking the weather to a bacterial brain infection?
It is a mechanical disruption of the human immune barrier. During the dry season, the hot, arid winds carry immense amounts of particulate dust. When humans inhale this dust constantly, it physically damages and desiccates the mucosal lining of the nasopharynx. Many people carry Neisseria meningitis asymptomatically in the back of their throats, but when the mucosal barrier is physically compromised by the climate conditions, the bacteria can invade the bloodstream, cross the blood-brain barrier, and cause explosive outbreaks of meningococcal meningitis. As climate change drives prolonged droughts further south, that geographic belt of vulnerability has enlarged to encompass regions like Uganda and Tanzania.
The opposite extreme of the climate spectrum is just as deadly. The textbook highlights the impact of extreme rainfall driven by the El Niño Southern Oscillation phenomenon. In 1997 and 1998, El Niño dumped massive, unprecedented amounts of rain across East Africa, causing extensive flooding.
The mechanism of emergence here involves the specific biology of the Aedes mosquito species native to that region, which are the primary vectors for the Rift Valley fever virus. These mosquitoes lay their eggs in dry depressions in the soil, known as dambos.
Right.
The eggs are remarkably resilient to desiccation and can survive dormant in the dry dirt for years waiting for water. The virus can actually be transmitted vertically from the adult mosquito to the egg, meaning the eggs themselves are infectious.
When the massive El Niño floods arrived, billions of these dormant, virus-laden eggs were suddenly submerged and hatched simultaneously. The environment was just swarming with infected vectors.
Simultaneously, the rising floodwaters physically displaced the local pastoralist communities and their large herds of cattle, sheep, and goats. Humans and livestock were forced to cluster tightly together on whatever small, elevated islands of dry land they could find.
A perfect storm.
You have a massive epizootic amplification in the crowded livestock, surrounded by an ocean of newly hatched, infected mosquitoes, with humans trapped in the middle. The mosquito efficiently transferred the Rift Valley fever virus from the amplifying animal host to the humans, resulting in the largest outbreak ever reported in East Africa, an estimated 89,000 human infections and nearly 500 deaths in northern Kenya and southern Somalia alone. The climate altered the terrain, hatched the vector, and corralled the hosts.
The climate displaces the animals, and the climate displaces the humans, which logically transitions us to Section 4, the darkest, most volatile factor in the textbook: human behavior, conflict, and crisis. Because humans don't just displace wildlife, we displace each other, and occasionally we intentionally engineer harm.
The intersection of public health and geopolitics is undeniable. War, civil conflict, and large-scale human displacement systematically dismantle the architectural resilience of a society. When populations are forced to flee violence on a massive scale, they almost invariably concentrate in improvised, impoverished refugee settings.
Environments characterized by acute overcrowding, profound malnutrition, and a total absence of sanitary infrastructure.
Exactly. The textbook directs our attention to the aftermath of the Rwandan genocide in 1994. Millions of Rwandans fled across the border into refugee camps in Goma, in the Democratic Republic of Congo. The volcanic terrain around Goma made it nearly impossible to dig proper latrines. The camps were built on solid rock. Hundreds of thousands of traumatized, malnourished people were relying on contaminated surface water.
And from a microbiological perspective, it was the perfect environment for Vibrio cholerae. Cholera is an acute diarrheal illness caused by infection of the intestine. The bacteria produces a potent enterotoxin that forces the mucosal cells of the gut to secrete massive amounts of fluid and electrolytes.
Right.
A patient can lose liters of water in hours, leading to rapid, fatal hypovolemic shock. Because the transmission is strictly fecal-oral, the lack of latrines and clean water in the Goma camps created a terrifyingly efficient transmission loop. Over 48,000 cases of cholera and nearly 24,000 deaths were reported within a single month.
24,000 deaths in 30 days. The sheer speed of that systemic collapse is hard to conceptualize. We witnessed a similar catastrophic vulnerability to cholera following the earthquake in Haiti in 2010.
Oh, right.
The Haitian disaster demonstrates the vulnerability of an immunologically naive population. Prior to the earthquake, cholera had not been documented in Haiti for over a century. The population had zero acquired immunity. The massive earthquake destroyed the nation's already fragile water and sanitation infrastructure.
And then it was introduced from outside.
Yes. When Vibrio cholerae was inadvertently introduced into this devastated environment by international personnel assisting with recovery, the pathogen faced no resistance. It swept through the river systems and the displaced population camps, eventually causing over 600,000 infections and 7,500 deaths, impacting roughly 6% of the entire country's population.
Conflict doesn't just create refugee crises. It actively degrades the medical facilities required to mount a defense. Look at the Marburg virus outbreak in Angola in 2004. Marburg is a filovirus in the same family as Ebola. It causes a similarly devastating hemorrhagic fever.
Right. Angola had endured a brutal 27-year civil war. The collateral damage of that prolonged conflict was the total degradation of the national health infrastructure. Hospitals were starved of funding, equipment, and trained personnel for decades.
So they were completely unprepared.
When the Marburg virus emerged, likely from a bat reservoir, the initial cases were misdiagnosed. The surveillance system was blind. When severely ill patients were finally brought to the pediatric ward of the provincial hospital in UH, the facility lacked the fundamental tools for viral hemorrhagic fever barrier nursing. No isolation wards, no reliable supply of sterile gloves, no safe protocols for handling heavily infectious corpses.
The hospital, stripped of its defenses by war, became the primary site of amplification. The virus spread rapidly among patients, their families, and the healthcare workers trying to save them. The outbreak infected more than 250 individuals, and the case fatality rate exceeded 90%. War dismantled the architecture, and the virus exploited the ruins.
It really is a tragic pattern.
Let's pivot from massive societal collapse to a much more granular level of human behavior: occupational exposure. The routine tasks humans perform to survive frequently place them directly in the crosshairs of emerging pathogens.
Yes. The history of infectious disease is intimately tied to occupation. Anthrax, caused by the spore-forming bacteria Bacillus anthracis, is classically known as wool sorter's disease. The bacteria naturally exists in soil and infects grazing herbivores.
And when the animal dies?
When the animal dies, the bacteria forms incredibly resilient spores that contaminate the hide and fleece. During the Industrial Revolution, humans working in crowded, poorly ventilated mills, mechanically sorting and processing these infected fleeces, would aerosolize the microscopic spores.
And the pathophysiology of inhalation anthrax is just brutal. The spores are drawn deep into the alveoli of the lungs. They are ingested by macrophages, which essentially act as Trojan horses, carrying the dormant spores to the regional lymph nodes. There, the spores germinate into active bacteria, multiply rapidly, and release deadly toxins that cause massive hemorrhage, edema, and tissue necrosis. The mortality rate without rapid intervention is extremely high.
And we see identical patterns of occupational risk driving the emergence of novel viruses today. The textbook traces the epidemiology of several Ebola outbreaks directly to specific economic activities deep in the forest ecotone.
Like what?
In 1995, in Kikwit, the index case was a woodsman making charcoal deep in the tropical rainforest, a profession that placed him in direct contact with the habitats of bats and non-human primates. In 1996, in Gabon, the outbreak began with a group of young hunters who butchered a chimpanzee found dead in the forest. In 2008, in Uganda, transmission was definitively linked to gold miners working in caves heavily populated by fruit bats, exposing them to massive amounts of aerosolized guano.
And looking at avian influenza, specifically the highly pathogenic H5N1 strain, human infections are almost exclusively confined to populations with intimate occupational exposure to poultry. We are talking about individuals who raise backyard flocks, workers in massive industrial poultry processing plants, and the veterinarians dispatched to investigate sudden die-offs in those flocks. The occupation dictates the risk profile.
That's entirely correct.
But there is another facet of human behavior detailed in the text that doesn't involve handling bats or living in a war zone. It is a cognitive vulnerability that fundamentally undermines public health architecture: the devastating impact of misinformation.
And the text forces us to analyze misinformation not as a political issue, but impartially, as an epidemiological variable. Trust is the invisible mortar that holds public health infrastructure together. When trust fractures, the system fails mechanically.
Can you give an example?
The textbook highlights the crisis in northern Nigeria in 2003. A massive global effort was underway to eradicate polio. But unsubstantiated rumors began circulating rapidly in the region that the oral polio vaccine was unsafe, that it was contaminated with HIV, or that it was designed by Western powers to cause infertility in Muslim populations.
So misinformation is essentially a pathogen itself. It infects the mind, alters behavior, and causes a measurable physical outcome in the population. The mistrust generated by these rumors led the local political leadership to officially suspend polio immunization campaigns in 2 key northern states for nearly a year.
And the epidemiological consequence of that suspension was mathematically inevitable. Polio is an enteric virus, spreading via the fecal-oral route. To maintain herd immunity and prevent transmission in dense populations, you need a vaccination coverage rate exceeding 85 to 90%. When the campaigns halted, the proportion of susceptible children in the population quickly rose above that critical threshold.
The virus found its opening.
Exactly. The virus, which had been cornered, found these expanding pockets of vulnerability and surged.
It resulted in a massive resurgence of paralytic polio across northern Nigeria. But because diseases do not respect borders, it didn't stay there.
Yeah.
The Nigerian outbreak functioned as a massive viral exporter.
Right.
The virus swept outward along travel and trade routes, reinfecting previously polio-free countries across West Africa, across the Sahel to Sudan, across the Red Sea into Yemen and Saudi Arabia, and eventually reaching all the way to Indonesia.
The textbook underscores the tragedy with a chilling statistic. By 2004, over 70% of all children worldwide who were newly paralyzed by polio were either living in Nigeria or were infected by a viral strain that was genetically sequenced and directly linked to the Nigerian outbreak. A collapse in local trust unraveled a decade of global eradication progress.
And this structural vulnerability to misinformation is not confined to developing nations. The textbook points directly to the MMR measles, mumps, rubella vaccine scare in the United Kingdom.
In 1998, a British medical journal published a study, which was later thoroughly discredited, fully retracted, and deemed fraudulent, that falsely suggested a causal link between the MMR vaccine and the development of autism in children. The intense, sensationalized media coverage of this fraudulent claim caused public confidence in the safety of the vaccine to completely collapse.
And again, the math is unforgiving. Measles is one of the most contagious respiratory viruses known to humanity. It has an R0 of 12 to 18, meaning one infected person in a totally susceptible population will infect 12 to 18 others.
It's incredibly transmissible.
To prevent measles from spreading, you need a population immunity level of roughly 95%. Following the scare, vaccine uptake in parts of the UK plummeted from a safe 92% down to a low of 79% by 2003.
And when coverage drops to 79% for a pathogen with that level of transmissibility, outbreaks are a biological certainty. The UK, which had virtually eliminated endemic measles, saw a resurgence of the disease, resulting in severe hospitalizations and entirely preventable deaths. Public confidence is a load-bearing pillar of the epidemiological architecture.
Which brings us to the final and undoubtedly most chilling behavioral threat discussed in the chapter: the deliberate weaponized use of pathogens, bioterrorism. The intentional dissemination of infectious agents to cause terror, destabilize governments, and inflict mass casualties.
The textbook provides 2 critical modern case studies to understand the mechanics of this threat. The first is the Sverdlovsk anthrax leak in the former Soviet Union in 1979. Initially, the Soviet government attributed a sudden cluster of fatal anthrax cases to the local population consuming contaminated meat.
But that wasn't true.
No. Epidemiological investigation eventually revealed the truth. It was an unintentional release of aerosolized anthrax spores from a military microbiology facility known as Compound 19.
A technician had briefly removed a clogged exhaust filter from the ventilation system and failed to replace it or properly log the removal. During the next shift, the machinery was turned on and a plume of microscopic weaponized anthrax spores was vented directly into the outside air.
The physics of aerosolization is the key variable in bioterrorism. To cause mass casualties via inhalation anthrax, the spores must be milled down to a highly specific, respirable size, typically between 1 and 5 microns.
Why that size?
If they are larger, they get trapped in the upper respiratory tract. If they are smaller, they are simply exhaled. The wind caught this perfectly weaponized plume and carried it over the city. It infected an estimated 358 people, causing up to 199 deaths downwind of the facility.
The second textbook example brings the threat out of the Cold War and into the modern era: the 2001 U.S. postal anthrax attacks.
Yes. In the weeks following the September 11th terrorist attacks, letters containing highly refined, easily aerosolized anthrax spores were mailed to news media offices and the offices of 2 U.S. senators. 22 people were infected. 11 developed the less severe cutaneous form of the disease through skin contact. The other 11 developed the highly lethal inhalation form. 5 people died.
But the crucial systemic takeaway from the 2001 attacks is who was infected. The text highlights that 20 of the 22 patients were exposed at contaminated work sites, and 9 of them were postal workers operating the mail processing facilities.
Right.
The perpetrators didn't need to build a complex dissemination device. They simply co-opted the existing logistical infrastructure of the country. The high-speed mail sorting machines mechanically squeezed the envelopes, aerosolizing the spores and pumping them into the facility's HVAC systems. The critical infrastructure itself became the vector.
And this reality leads the textbook to a profound discussion on the dual-use dilemma of modern laboratory research. The text specifically highlights controversial gain-of-function research involving the highly pathogenic H5N1 avian influenza virus. Scientists in highly secure laboratories intentionally engineered mutations into the H5N1 genome to see what specific genetic changes would allow the virus to transmit efficiently via respiratory droplets between mammals, specifically ferrets, which are the standard animal model for human influenza.
As someone studying public health, this concept is simultaneously fascinating and terrifying. We have brilliant scientists actively engineering a pathogen to be more transmissible. The rationale is that by building the threat in the lab, we can map the exact mutations required for a pandemic.
Exactly.
We are trying to build a better early warning radar for our surveillance of wild bird populations, and we are trying to preemptively design matching vaccines. But by doing so, we're literally synthesizing the hazard itself. How does global public health balance that scale?
That is the exact tension of the dual-use dilemma. The research holds immense potential benefit for global preparedness. However, the exact same knowledge, if published openly, provides a blueprint for malicious actors. Furthermore, even in the most secure biocontainment facilities, the risk of accidental laboratory-acquired infection or a breach in containment is never mathematically zero.
Right.
It is an existential tightrope walk, trying to peer into the evolutionary future of a virus without accidentally unleashing that future upon the present population.
So we have the futuristic James Bond-level threat of lab-engineered pandemics on one side. But the truth is, we don't need a high-tech bioweapons lab to engineer superbugs. We are actively engineering them completely by accident every single day in our local hospitals and on our industrial farms. The pathogens are mutating naturally right under our noses. This brings us to Section 5 of the text, the evolutionary arms race, more formally known as antimicrobial resistance, or AMR.
It is vital to frame AMR correctly. Antimicrobial resistance is not a moral failure of modern medicine. It is an absolute inevitability of biological evolution under immense selective pressure. Bacteria, viruses, fungi, and parasites are constantly replicating, and as they replicate, they undergo spontaneous genetic mutation.
And the mechanisms they develop are incredible. Bacteria can mutate to produce enzymes like beta-lactamases that literally chop up the antibiotic molecule before it can work.
Yes.
They can alter the structure of the target site on their cell wall so the drug can't bind. They can even build microscopic efflux pumps in their cell membranes that actively pump the antibiotic back out of the cell as fast as it enters.
Exactly. Now, consider the environment we place them in. When a human patient takes an antibiotic, the drug effectively kills off the billions of susceptible bacteria. But if, by random chance, just one of those bacteria possesses a genetic mutation that allows it to survive the drug, that single resistant organism is left standing in an environment devoid of competition.
It has a free pass.
Right. It multiplies rapidly. We have created a survival of the fittest scenario on an accelerated timeline. Furthermore, bacteria can share these resistance genes with entirely different species of bacteria through a process called horizontal gene transfer, exchanging small circular pieces of DNA called plasmids. The resistance spreads across the microbial chessboard.
And the speed at which the microbes adapt is terrifying. The textbook highlights methicillin-resistant Staphylococcus aureus, or MRSA. Methicillin was introduced to the clinical market in 1960 as a powerful new weapon against penicillin-resistant staph infections. MRSA, a strain that had mutated as penicillin-binding proteins to evade the new drug, emerged in the UK in 1961. It took the bacteria less than a year to crack the code.
The microbes are deeply resilient, and our chemical arsenal is finite. The text points to several critical contemporary threats. Since 2008, the global medical community has tracked the rapid dissemination of carbapenem-resistant enterobacteriaceae, or CRE, originating in Asia.
And carbapenems are the big guns, right?
Yes. Carbapenems are broad-spectrum, intravenous antibiotics, often considered the absolute last line of defense against severe, multi-drug-resistant bacterial infections. The bacteria are now producing carbapenemase enzymes that destroy our final safety net.
We are seeing this resistance across all classes of pathogens. We are dealing with extensively drug-resistant tuberculosis, or XDR-TB, which caused a devastating outbreak in KwaZulu-Natal, South Africa in 2006. The textbook notes that this outbreak was heavily linked to HIV co-infection.
Which makes sense.
Right. A population with severely compromised immune systems provides the perfect, unopposed training ground for the mycobacteria to mutate and develop resistance to multiple first- and second-line anti-TB drugs. We are even tracking the emergence of artemisinin-resistant malaria in the greater Mekong subregion of Southeast Asia, a development that threatens to completely derail 2 decades of global malaria control efforts.
So biological mutation is inevitable. But the textbook isolates 2 massive human drivers that are effectively pouring gasoline on this evolutionary fire: the misuse of antimicrobials in human medicine and the indiscriminate use of anti-infectives in agriculture.
Let's examine human medicine first. Overprescribing is a systemic behavioral flaw in clinical practice. The text cites a historical study from a university hospital in Thailand in the late 1980s, which found that 36% of patients treated with antibiotics did not actually have an infectious disease that warranted them.
36%.
Yes, they were being prescribed for viral infections, like the common cold, against which antibiotics are completely useless. Or they were prescribed purely prophylactically out of an abundance of caution by the physician.
And the data is consistent globally. A cited study from Canada estimated that up to 50% of all antibiotic prescriptions in the community setting were unnecessary or inappropriate in their choice of drug or duration. Every single inappropriate prescription is an unforced error. It is a free training session that exposes the patient's natural microbiome to the drug, selecting for resistance without providing any clinical benefit.
And then there's the agricultural driver. As someone who eats food, this mechanism is incredibly frustrating. Massive industrial quantities of anti-infective drugs are added to the feed and water of livestock, not to cure sick animals, but prophylactically to prevent disease in overcrowded conditions and, more insidiously, to promote faster weight gain and animal growth.
Subtherapeutic dosing in livestock is perhaps the most efficient engine for AMR we have ever devised. By feeding low doses of antibiotics to millions of animals continuously over their lifespan, you are perpetually exposing immense bacterial populations to non-lethal selective pressure.
It guarantees the selection and amplification of resistant strains.
Exactly, within the animal's gut. These resistant bacteria, or their resistance genes, are then transferred to human populations through the food chain via contaminated meat or through environmental contamination of soil and water via agricultural runoff. We share a single microbial pool with the animals we eat.
When you look at the math bacteria reproducing every 20 minutes, constantly sharing resistance plasmids, versus the pharmaceutical industry taking 10 to 15 years and billions of dollars to bring a novel class of antibiotics to market, it feels like we are fundamentally losing this arms race. I need some hope here. Is there any example where upstream engineering actually worked to reverse or stall AMR?
Yes, there is. The textbook provides a brilliant, counterintuitive example of successful upstream engineering from Norway's salmon and trout farming industry. In the late 1980s, the Norwegian aquaculture industry was facing massive bacterial outbreaks in their densely packed fish pens, and they were dumping heavy, unsustainable amounts of anti-infective drugs into the fjords to control the losses.
But instead of just passing a law banning the drugs and letting the industry collapse, they completely redesigned the architecture of the farms.
Precisely. They engineered the health of the host. The industry, working with scientists, developed and introduced highly effective injectable vaccines against the primary bacterial pathogens threatening the fish. They fundamentally improved the health management protocols, optimizing the density of the pens and the water flow to reduce stress on the animals. By removing the biological vulnerability of the fish, they completely eliminated the need for the chemical crutch.
And the result is staggering. By vaccinating the fish and improving husbandry, Norway reduced the annual use of anti-infective drugs in farmed fish by 98% between 1987 and 2004, while simultaneously massively increasing their overall fish production. Upstream engineering at its absolute finest. If the host doesn't get sick, you don't pour antibiotics into the water, and the bacteria are denied their evolutionary training session.
That paradigm of upstream prevention forms the core of the World Health Organization's global containment strategy for AMR. It is a multi-pronged approach that demands rational drug use in clinics, stringent infection prevention and control in hospitals, clean animal husbandry without growth promoters, robust laboratory surveillance networks to track resistance patterns, and sustained investment in research and development for new diagnostics and therapeutics.
But implementing a strategy of that magnitude requires a level of coordination that transcends national borders. Because as we've established today, whether it is a brilliant vaccine policy in Norwegian fish farms, a doctor overprescribing in a clinic in Thailand, or the collapse of a hospital ward in Angola, highly localized actions instantly ripple out to have profound global consequences. We're all swimming in the same microbial pool.
Which means we cannot simply rely on the competence of individual nations acting in isolation. We need a binding global rulebook. The architecture of preparedness requires a legal foundation. That brings us to Section 6 of the textbook chapter, Global Governance and the International Health Regulations.
To understand the modern legal framework, we have to trace the history of global public health security. Our attempts to legislate against disease actually date back centuries. The textbook notes that in the 14th century, the city-state of Venice, a massive hub of global trade, recognized that incoming merchant ships were acting as vectors for the bubonic plague.
Though they didn't understand the microbiology of Yersinia pestis or the role of the rat flea, they understood the epidemiology of time and isolation. The Venetian authorities legislated that arriving ships suspected of carrying disease had to anchor offshore for 40 days before the crew or cargo could unload.
Right.
The Italian word for 40 is quaranta, which is the etymological origin of the word quarantine.
It was a strategy based entirely on rigid border control. Stop the ship, stop the disease. And that specific mindset persisted for a remarkably long time. And the textbook discusses the series of international sanitary conferences held between 1851 and 1897.
European nations convened these conferences primarily to establish cooperative agreements on how to keep cholera, plague, and yellow fever out of their territories without completely strangling international maritime trade. The interventions agreed upon were almost entirely focused on passive measures at the borders quarantines, the telegraphic notification of outbreaks, and the inspection of ships.
This philosophy eventually culminated in the 1969 International Health Regulations, the IHR. But the textbook makes it very clear that the 1969 iteration of the IHR was a fundamental failure in the modern era. Why did the border wall strategy collapse?
The 1969 IHR failed because it was rigidly narrow and scientifically outdated. First, it legally required member states to report outbreaks of only 4 specific diseases: cholera, plague, yellow fever, and smallpox. If a novel virus emerged, the regulations essentially ignored it.
Wow, that's short-sighted.
Second, the primary mechanism of intervention was still pre-established control measures at international borders, ports, and airports. By the late 20th century, the volume and velocity of international air travel had rendered border checks obsolete.
A commercial jet crosses the Atlantic in 6 hours. The incubation period for most respiratory viruses is several days. An infected traveler walks through the thermal scanners at the border looking perfectly healthy, passes customs, and develops a cough 3 days later while riding the subway in a new city. A border post is physically incapable of stopping an incubating virus. It's like trying to catch water with a sieve.
Furthermore, the 1969 regulations relied entirely on the honor system. Governments were supposed to self-report outbreaks to the World Health Organization. But we just discussed the economic modeling. If a country reports an outbreak of plague or cholera, other nations immediately slam their borders shut, ban their agricultural exports, and cancel tourism. The economic punishment for transparency is devastating.
So they just hid it.
Consequently, nations simply stopped reporting. They actively hid their data from the WHO to protect their economies, allowing outbreaks to silently expand until they breached borders anyway.
The system was broken. So from 1996 through to 2005, the member states of the WHO undertook a massive paradigm shift, completely rewriting the rulebook to create the IHR 2005.
The 2005 regulations represent a profound shift in epidemiological philosophy. The global community recognized that passive border control was useless. The new IHR moved toward an active upstream model. It legally requires all 196 member states to build and maintain fundamental core capacities for public health surveillance and response at the local and national levels. The mandate is to detect the spark at the source, rapidly assess it, and extinguish it before it ever reaches an international airport.
The 2005 IHR introduced a crucial new concept, the PHEIC, the Public Health Emergency of International Concern. To determine if an outbreak constitutes a PHEIC, the regulations provide a specific decision tree algorithm. And if you are a clinician listening to this, you need to pay attention because you are the boots on the ground feeding data into this algorithm.
Let's walk through the clinical application of that algorithm. Imagine you are a physician in a rural clinic and you observe a sudden cluster of severe, undiagnosed hemorrhagic fevers. You run it through the decision tree. First, is the public health impact of the event serious? Yes, patients are dying. Second, is the event unusual or unexpected for your region? Yes, you've never seen these symptoms before.
Okay, what's next?
Third, is there a significant risk of international spread? If your clinic is near a busy border crossing, yes. Fourth, is there a significant risk that the event will provoke international travel or trade restrictions? Absolutely. If the event meets any two of these criteria, the national government is legally obligated under international law to notify the WHO within 24 hours.
And the textbook outlines a fast-track list, right? 4 specific diseases that are considered so inherently dangerous that a single diagnosed case completely bypasses the algorithm and mandates immediate notification to the global community.
Yes. The always notify list. A single case of smallpox, which would indicate a terrifying breach of the eradication containment. A single case of poliomyelitis caused by a wild-type poliovirus, threatening the global eradication effort. A single case of human influenza caused by a completely new virus subtype, signaling pandemic potential. Or a single case of severe acute respiratory syndrome, SARS.
Just one case.
One confirmed case of any of those 4, and the global alarm is pulled instantly.
And it was exactly the SARS outbreak in 2003, the doctor in the Metropole Hotel in Hong Kong, that finally forced the international community to adopt these sweeping 2005 changes. The speed at which SARS utilized the global aviation network to seed outbreaks on multiple continents simultaneously proved that the 1969 rules were dangerously obsolete.
SARS proved that we needed real-time clinical evidence, rapid local detection, and an internationally coordinated response mechanism that wasn't paralyzed by bureaucratic delays. But the most revolutionary aspect of the IHR 2005 directly addresses the issue of governments hiding data out of economic fear. The 2005 regulations explicitly acknowledge and empower non-state sources of information.
This is a massive geopolitical shift. It means the WHO doesn't just have to sit back and wait for an official, politically sanitized press release from a reluctant government ministry.
Precisely. The WHO is now legally authorized to continuously monitor global digital surveillance networks like the Global Public Health Intelligence Network, GPH, or ProMedMail. If a national government is attempting to suppress the news of a novel respiratory outbreak, but a network of brave local doctors, academic laboratories, or international NGOs are sounding the alarm online, the WHO can use that unofficial data to formally approach the member state, demand verification of the event, and offer immediate technical assistance. It essentially crowdsources global surveillance, empowering the vigilance of local clinicians over the political calculations of the state.
So the entire legal framework ultimately relies on shared responsibility in the face of universal vulnerability.
That is the ultimate conclusion of the chapter. We reside in an incredibly dense, hyper-interconnected global ecosystem. An outbreak of a novel virus in a remote village, or the emergence of a multi-drug-resistant bacteria in a pristine hospital, is a threat to everywhere simultaneously. Global preparedness is not about building an impenetrable wall at the border. It is about constructing a sensitive, resilient global nervous system capable of detecting the microscopic shifts in the environment and possessing the architectural surge capacity to respond effectively.
Let's synthesize the blueprint we've mapped out today. We are living in the seismic zone. We've established that the tectonic plates of emerging pathogens are driven primarily by ecological and social changes. When we aggressively bulldoze the ecotone, forcing wildlife into contact with livestock, the forest pushes back with novel zoonotic spillovers.
Yes.
They've seen how our modern, crowded urban infrastructure and our unparalleled global travel networks act as massive amplification engines for these pathogens. We've explored how conflict, collapsing healthcare infrastructure, and the insidious spread of misinformation actively dismantle our defenses. And finally, we've seen that our only viable strategy relies on robust, early warning surveillance, the careful stewardship of antimicrobials, incredibly strong local health systems, and seamless, transparent international coordination governed by the IHR 2005.
It represents a profound, necessary evolution from the reactive practice of emergency medicine to the proactive, architectural discipline of global public health.
Now, before we run through our rapid recall prompts, I want to leave you, the listener, with a final provocative thought. A scenario to mull over during your next night shift or your commute home. We have talked extensively today about spatial disruption, deforestation, and urban encroachment, bringing us into contact with new pathogens hidden in the deep forest. But consider temporal disruption. What happens when the aggressively warming climate begins to systematically melt the massive permafrost layers in the Arctic?
Oh, that's a chilling thought.
We are potentially talking about unlocking ancient, dormant pathogens, microbes, viruses, and massive DNA viruses that have been frozen in the ice for tens of thousands of years. Pathogens that infected Neanderthals or megafauna. Humanity has absolutely zero evolutionary memory, zero residual immunological defense against these ghosts from the deep past. Our current IHR 2005 frameworks are brilliantly designed to track the rapid RNA mutations of present viruses. But are those systems structurally adaptable enough to detect, characterize, and contain an ancient pathogen whose biology we haven't even conceptualized? Just something to think about as you study the architecture.
A chilling and highly relevant thought experiment for the future of global health security. Now, let's actively reinforce the frameworks we've discussed today with our rapid single best answer recall prompts. Listeners, test your attention. I will read the question, I'll pause briefly, and then I'll provide the correct answer and the specific section of the Oxford chapter you should revisit for consolidation. Here we go. Question 1. Under the International Health Regulations 2005, a single case of which of the following diseases must always be notified to the WHO, entirely bypassing the decision tree algorithm? A. Ebola. B. Cholera. C. Human influenza caused by a new subtype. D. Yellow fever. Take a second to think about it.
Lock in your answers.
The answer is C. Human influenza caused by a new subtype. To consolidate this mechanism of global governance, review the IHR 2005 section and Annex 2 of the chapter. Question 2. The 2009 H1N1 influenza pandemic virus emerged rapidly due to which specific genetic mechanism? A. Antigenic drift via polymerase errors. B. Genetic reassortment of swine, avian, and human RNA. Segment C. A single point mutation in an avian host alone. Take a moment.
Hopefully you got that one.
The answer is B. Genetic reassortment of swine, avian, and human RNA segments. The mechanics of this viral shift are detailed in the section on infections with sustained transmission. Question 3. Which specific anthropogenic activity was the direct epidemiological driver for the emergence of the Nipah virus in Malaysia? A. Clearing deep forests for agriculture, forcing fruit bats into dense pig farming areas. B. The massive use of anti-infectives in commercial fish farming. C. Extreme flooding driven by the El Niño Southern Oscillation. I'll give you a second.
Think about the bulldozer.
The answer is A. Clearing deep forests for agriculture, forcing fruit bats into dense pig farming areas. Review the section on anthropogenic activities to review the ecotone risk. Question 4. What was the primary systemic driver for the devastating reemergence of diphtheria in the Russian Federation in the early 1990s? A. The catastrophic failure in municipal water sanitation. B. Severe lapses in childhood immunization programs causing a drop in herd immunity. C. Uncontrolled nosocomial spread within hospital wards. Take your time.
This one goes back to the beginning of our chat.
The answer is B. Severe lapses in childhood immunization programs causing a drop in herd immunity. This highlights the vulnerability frameworks discussed in the Weekend Public Health Infrastructure section. Question 5. How did the nation of Norway successfully engineer a 98% reduction in antimicrobial use in farmed fish between 1987 and 2004? A. Banning all commercial fish farming operations. B. Introducing highly effective fish vaccines and fundamentally improving health management husbandry. C. Switching the entire industry from antibacterial to antiviral medications. Final question. Take a second.
The great success story.
The answer is B. Introducing highly effective fish vaccines and fundamentally improving health management husbandry. Revisit the section on the use of anti-infective drugs in agriculture for the details of this upstream engineering success.
Excellent work today. Remember, as you walk the wards tomorrow, or as you sit down to analyze population data sets, you are not merely looking at isolated clinical cases or random data points. You are observing the tectonic plates of public health shifting in real time. You are a critical component of the early warning radar. Preparedness is not about waiting for the earthquake to strike. Preparedness is architectural. Here are the details of this episode.
Emerging infections. Byline. Novel pathogens, globalization, and preparedness in an interconnected world. Odoreo episode description. Emerging infections represent one of the most dynamic and unpredictable areas of public health. Novel pathogens, zoonotic spillovers, antimicrobial resistance, and ecological disruption continuously reshape global disease landscapes. This episode examines drivers of emerging and re-emerging infections. This episode examines zoonotic spillover and wildlife-human interfaces. This episode examines urbanization, travel, and global connectivity. This episode examines climate change and vector redistribution. This episode examines early detection and surveillance systems. This episode examines genomic sequencing and pathogen identification. This episode examines health system surge capacity. This episode examines risk communication during uncertainty. This episode examines international health regulations and global governance. This episode examines emerging infections demonstrate how rapidly local outbreaks can become global crises. Air travel, dense urban populations, and environmental disruption accelerate transmission. Preparedness, therefore, depends on surveillance, rapid diagnostics, laboratory networks, and coordinated international response. This episode examines. The episode highlights the importance of resilience-building systems capable not only of responding to known threats, but of adapting to unknown ones. This episode examines. Preparedness is not reactive, it is architectural. This episode examines. This episode examines. Key takeaways. This episode examines. Emerging infections arise from ecological and social change. This episode examines. Zoonotic spillover is a major source of novel pathogens. This episode examines. A global travel accelerates spread. This episode examines. Surveillance and early detection are critical. This episode examines. Genomic technologies enhance outbreak tracking. This episode examines. Strong health systems improve resilience. This episode examines. International coordination is essential for containment.